nails are manufactured by the drawing process, its initial diameter is 15 millimeters. So if I write down the initial diameter, which is dB, it is 15. So this is my dB. So let me write down dB is 15 millimeters, and the steel has the strength coefficient K equals to 625 megapascal, and N, the strength coefficient, it is 0.14, and the friction coefficient and the die angle, which is this over here. This is die angle, and in our case, this is 5 degrees. The machine has a motor with a power. So there's a motor which is pulling this. The motor is pulling somehow this wire over here with some mechanism, and the power of the motor is 35 kilowatts. And the question is, find the minimum diameter dA. The answer is dA 10 millimeter. But how would you get 10 millimeter? I will show you in a bit. And what is the speed? The maximum. The second question is, this is our A part, the B part, but we have to find out. But I will show you the answer in a bit. The second part is drawing speed. So if the power is given, then the force times the speed is also known as the power. Agreed? So let me grab a formula for the minimum uh, diameter. So let me grab it over here. So this is my formula. So I'm going to show you how to use this formula. And in this case, since it is not mentioned, what is our back stress, sigma xb? If it is not mentioned, you will assume sigma xb, this term is 0. Sigma xb equals to 0. And in order to find out this minimum diameter, we assume that the 2 tau flow, what is this? This is the required stress according to the Tresca, that it should be equal to the shear stress should be equal to the average yielding stress, which is equal to this one. This is my formula for average uh, flow stress when the materials start plastically deform. And over here, the power law, the sigma equals to K times epsilon to the power n. So let's do this over here. I'm going to show you what is my B. B equals to mu over tangent alpha. It's a constant. It's for our convenience. You can write down C, D, whatever it is, but let's assume this is B, since our note says is B mu over tangent alpha, the die angle. What is our mu? If you take a look, mu is 0.1. Open your calculators and let me know what is my B value. Tangent alpha is 5 degrees. Can you help me? What is my B value? One student says it is 1.14. Do you verify? He says he verifies. So that's good. So we have to plug it in over here. So let me write down the whole formula again. Sigma xa, which is sigma xa over tau flow, 2 tau flow, which is the shear stress. It requires shear stress to let the material flow. And shear stress is equivalent to the average. This is according to our more stress circle Tresca requirement. Okay, now over there I will write down 1 plus B over B and 1 minus diameter extruded diameter over the initial diameter raised to power 2b. So since we don't have the backflow stress, so we are good. This term, the second term, is 0. You agree with your professor? So let's plug it in. So before I plug it in, you will help me. So what is 2 tau flow? What is y yielding stress? Average yielding stress equals to K times epsilon to the power n or n plus 1. So let me write down over here this whole formula. You will see. I'm going to plug in the values here before I find out the answer here. I'm going to plug it in. So sigma x a k equal k epsilon to the power n, k epsilon to the power n over n plus 1. Agreed? 1 plus 1.4, 1.14. We already calculated that. 1.14, 1 minus dA. I will say minimum. Below this value, you cannot achieve with this diangle. You cannot achieve the diameter below this value. So that's why we call it as a minimum. D initial diameter, which is dB at the back side, or B, it is 15 millimeter. Agreed? So let me plug it in over here. 15 power 2 times 1.14. Now we will do the math here. Look, cancel out this n1 and plus 1 goes onto the right side, or n plus 1. I can write down here. Can I write down like this? Uh, 1 plus b over b. What is my n value? N value is 0.14. So can I bring in cross multiply? If you consider this, let's cross multiply it. 1. Agreed? Now can you sorry, n equals to how much is n? 1 0.14. Agreed? So now everything is here. So let's do this. I'm going to show you 2.14 divided by 2.14 divided by 1.14. This is the value for 1b. So divide this value divided by 1.14. Agreed? So this is the multiplicating factor with this one. So I'm going to write down this one here. 1 equals to 1.6, let's say 646, and then minus 1.646 times dA over 15 times 2 times agreed. So now we just have to do some math and find out the answer. Can you open your calculators and help your professor here? 1.1 minus 1.646 negative 6 divided by 1.646.4, about 0.392. So let's write down over here 0.392 equals to dA over 15. Agreed? So what I'm gonna do here, 0.392 raised to power 1 over 2.28. 0.66. So let me write down here point dA over 15, 0.663. So let me do over here 0.663 times 15. About 10. That's what little bit decimal place is okay. Okay. Do you get this answer? 10. That's good. So below this diameter, you cannot achieve with this diangle and with this friction coefficient, you cannot achieve that. So you have understood how to find out the minimum diameter? About 10 millimeters. Have you understood up until here? Okay, after this, you will use the same formula. I'm going to use the same formula, and I will also use this Y flow. Let me show you. You will help me. Open your calculators, and I wanna do the second part here. Second part here. I wanna do the same formula here. Look over here. Now, what I need what I need from you, find out sigma xa. If you find sigma, which is a pressure, pressure equals to force per unit area. Agreed? And here the area is the final extruded area. And if you take a look, extruded area, this is sigma xa equals to force, the drawing force, drawing force times pi by 4 dA square. Agreed? And now we are going to use this sigma xa. You will help me. Sigma xa. Let's find out what is two-tau flow. Two-tau flow, the shear stress according to Tresca equals to the average yielding stress, K times epsilon. Do we have epsilon? No, we don't. But we can calculate it. Epsilon for our drawing process is equal to area final, area initial, or area initial. I would say like this: 2 times ln and what is my, you remember the volume consistency? We did that before for the height and for the diameter, area and volume consistency, because for epsilon, the true stress is also equals to ln a final length over initial length in case of the uniaxial stress. You remember, sample has been taken, so we have to be consistent. You remember that volume is consistent, so we do that. So that is equal to 2 ln dB. What is dB? So final initial diameter is 15. Agreed? And the final diameter is 10. Can you open your calculators rather than me? Can you do the math for your professor? Yes, what is that? One student says 0.81. You agree? You agree? Okay, now let's plug it in this. I'm gonna look over here. What is my K value? In the question, it is stated that the K strength coefficient is 625. Okay, and is 1.14. So let me write down over here. So let me write down here. Average yielding stress equals to 625 megapascal times 0.81 raised to power 0.14 divided by n plus 1, 0.14 plus 1. Can you open your calculator and help your professor? Do you get 532 megapascals? Just let's see whether you get the same. Yes, John, Michael, Thomas, you got the same? He says, yes, professor, he got it. So if you get this answer, so now you have completed this math of the denominator. We have to take this denominator, cross multiply with the right hand side. Okay, now the problem is becoming very easy for you. Very easy. So now let me bring this over here. Again, I'm going to write down this, and sigma xa, that is my objective, to find out the drawing stress, pulling stress at the A side, which is the front side, B side at the back side, which is so 1 plus B. So I can write down 532 times 1 plus 0.14 divided by 0.14. I'm sorry, this is 1.14. B equals to, yeah, 1.14. I forgot. This is 1.14. Please correct me if I do some mistake. And this is my 1.14. 1 minus diameter, the extruded diameter is 10 millimeter, the back diameter is 15 millimeter, and 2 times 1.14. Agreed? So can you do the math for your professor? Let me know how much do you get. Do you get about 602.5 megapascals? Please confirm. He confirms, you confirm, she confirm, he confirms. That's good. Very good, guys. Now you have approximately finished. The last part is coming, which is sigma. Our question states find out the speed, drawing speed. Look at here. The drawing speed is given. It's not given, but the answer has been already given to you for your help. So, but I will not give the answer in the exam. You will do it by yourself. Exam is on this Thursday. Okay, let's do this math together. So sigma, look, sigma equals to force per unit area, the drawing force, and area drawing in front of the. What is the drawing force? I would say let's F sub D. You will multiply by pi by 4 dA square. You agree with me? 602.5 megapascals, and then megapascal 10 to the power 6, and then pi by 4. Open your calculators, and diameter is 10 millimeters, so let's convert it into meters. How much do you get the force? You help me. What is the drawing force? Is it 47.3 kilonewtons? Let me see if you get the same answer, then I'll be happy. Yes? Arden says yes. Noah says yes. Thomas says yes. Henrik says yes. Dimitri says yes. That's good. Good job, guys. So now look, what is our question? Find the speed, the pulling speed. Now you see, look, I gave you this formula. You remember? And now can I use this formula? If you know the drawing force, if you know the power is given in the question. How much? 35 kilowatt for the motor. So can you find out the speed if you are given me the force, the power? Look, force has been found. So V equals to power divided by force. Drawing force equals to, so power equals to, how much is the power? 35. Yes, 35 kilowatts. 35 kilowatts, and divided by the drawing force is 47.3 kilonewtons. Kilo cancel. So open your calculators. Do you get 0.74 meters per second? Do you agree with your professor? Yes. Okay. So let me revise this review. Okay, if you see such a problem, you will start with finding the minimum diameter using the Tresca, which is the sigma flow, 2 tau flow equals to yielding, average yielding stress. When you have that much stress, it will be easily deformed. And then from there, you will find the minimum diameter. Have you understood up until here? Yes. And the next step, use the same equation. Now this time you will find the value of 2 tau flow or average yielding stress, and then find out the pulling stress, sigma xa, drawing stress, okay? And then stress equals to pressure, internal pressure equals to stress, okay? Force per unit area. Area, remember area is this side, not the back side. Area is the drawing side. Okay, you understood this point? And then from there, you can find out the drawing force. No, no. You have to assume only when it's not given. But if it is given that, but that's a good question. But I have given you the general equation. If in case if I give you sigma xb, then what would you do? You have to add this term. That was a good question by this gentleman. You understand this question? Now let me show you. Let me show you our homework problem. Homework problem is here. So over here, yes. The first question we already have solved in our class. So now this homework is due tomorrow. You will do at home with your own knowledge. I'm trying to explain to you in the classroom, but this is the homework problem number 1. Let me go over to the next problem. This problem. The second question is about the forging. And remember, we already solved this question in the classroom last time. You remember that? If I show you where is my forging, I think I solved this question at the end of the forging slides in the beginning. Yes, this was the question. And this is again coming in our homework problem. So you should be aware. I'm not going to solve it again because we already solved it and I have made a video on that. Okay. And then the final question. Plot external stress versus the diameter drawn from 9 millimeter to 13 millimeter. In this case, you will find out what is my sigma XA. And by the guy who asked me, but here in this case again, sigma XB. So can you find out sigma XA when the drawing stress, it goes from 9 millimeter and then 13 millimeter. I would say 12 millimeter because 13 is the initial diameter. But let's see, maybe 13 millimeter you will get zero stress if it is the same step. It's a drawing process. Okay, so can you first of all use this single value and then change the value here from 12 to 9. See what changes do you get. Can you find? You just have to use this equation. What this equation? Sigma XA 2 tau flow B, and everything has been given. B equals to mu over tangent alpha. Sorry, mu over tangent alpha. The die angle is 4. Can you solve this problem at home? You agree with your professor? Okay, let's do the extrusion. I want to show you the extrusion process now. Okay, let's do the extrusion. We did some of the problems, remember? No, we went over the theory. Do you remember that? Yeah, this one is for the direct extrusion. This formula. It should be in your formula sheet. I'm not going to test you from the extrusion process this Thursday. This will be in our quiz next week. And I will give you some solved problems so that you should also learn from the solution or the homework. But some problems you will solve by yourself, some problem I will give you. Is that okay? So let's do one problem here. Direct extrusion. Yes, this is the direct extrusion. The formula, there are two types of extrusion which you should learn. Direct extrusion, the ram comes from the back and the diameter is coming in the front. So let me show you. I believe this is my direct extrusion. This is the direct extrusion, okay? The pressure comes from the back and the the die, after the die you get the extruded part when the diameter, when the metal comes out of the diameter. But what if you, yes, what if you get the extrusion indirect? This is my indirect. The formula for indirect is little different, okay? It's a little bit different. So I'm gonna show you right now what is the formula. Yeah, I have to show you this figure. So this is for the pressure here, which can be calculated using this formula. And 2 tau flow, you already know this is the average yielding stress. Agreed? And RE, what is RE? It's a, yeah, reduction ratio, and that is equal to 1 over 1 minus R. Okay. So I would say RE equals to D1 square over D2 square. Because we know that reduction area in the drawing process is area back minus area forward over area back. Or you can write down like this. Or you can write down like this. 1 minus area final over area initial. And you know that, so from here, I want to show you this drawing process here. I think. This is for the drawing process. Okay, let's do one problem. Before I do, I want to show you LNRE. Extrusion ratio R sub E can be written like this: 1 over 1 minus RA. So it's not difficult. If you see our RA, reduction in area, is this much, I can prove it to you. How do we get this answer? This is my reduction area, and 1 over 1 minus AA over AB. Agreed? So what is 1 over 1 minus 1 plus area, front area, back? This is cancelled. So this AB goes into the numerator. AB over AA. Agreed? So what is area? Pi by 4 d square. Agreed? So I can write down here pi by 4 db square dA square, and this is cancelled. And if you take the ln of this one, this becomes the true strain, and this 2 is in the power, so 2 becomes the coefficient. As a logarithmic rule is the same thing which we are doing over here. This also equals to the true strain. And reduction area is this one. Okay, let's do one problem here. If I were you, I will prepare from the slides and the homework, because there is no recommended, no required textbook. But a student asked me, could it be a textbook which I could yes, it's a textbook, manufacturing process by Calpagian. So I will show you. It's freely available, so you can use that textbook. But right now I'm focusing on my slides. Okay, let's do this problem. You are forward cold extruding aluminum 1100 where the strength coefficient is given. So the K value is 140 megapascal and equals to 0.25, and the diameter, initial diameter, is 10 centimeters. Okay, so let me draw the rough sketch. Can you draw it with your professor? Like this, like this, and then the material comes out, and make sure it is at 45 degree. This angle, 45, 45, 90 triangle, because the maximum shear happens at 45 degree. So it will break at 45 degree, and this is my billet, complete billet. And this is the external friction, which we call X. You need that X in our formula. This one is, yes, over here. Yeah, if I show you what I need from, let's grab this one. I want to show you that what is my X? How can you calculate X? If the billet is 25 centimeter long, so I'm gonna show you if the billet is 25 centimeters long. So out of 25, how much is this portion? Suppose this is my X, okay? And what is this side? Suppose, and you will tell me this is my the initial diameter is 10 centimeters, okay? 10 centimeters, this is the initial diameter, and the final diameter is 5 centimeters. So the diameter is this diameter, 5 centimeter. The full extruded diameter, initial diameter is how much? 10 centimeter, and this is my X value. Okay, so D1 equals to 10 centimeter according to our notes. D2 equals to 5 centimeter. Let me grab another formula for your help. So if I go over here, yes, the direct extrusion. This is another thing. Both are correct. So if this is a 45-degree angle, how much is this side? Suppose this is side, uh, suppose this is side C. C equals to C. Can you tell your professor how much is C? It's a geometry. It's right angle triangle. What is this length? 10. What is this length? 5. And the remaining is 5 here. Sorry, 2.5 here, 2.5 here. You agree? So C equals to 2.5. You agree with your professor? And now you will tell me if the billet size, is how long is the billet? 25 centimeter. And 25 centimeter, and this one is how much? 2.5, and this one is my X. X equals to the total length minus dead zone. This is we call C is the dead zone. The material does not come out of the die. It keeps on staying there. That's why we call the dead zone. So what is my X value? Look, X equals to 25 minus 2.5. Agreed? How much is it? 22.5. You agree with your professor? So I'm just trying to gather some unknown variables to plug it in. Because my question states, determine the extrusion force and the power. Yes? So let me show you. The extrusion force is the force equal pressure times area. So extrusion force is extrusion pressure. Extrusion pressure is this much. This is my extrusion pressure. I would say Px. Can you help me finding out the Px? K epsilon to the power. I'm writing down the formula, and you will help me. 1.707 ln Re. Well, let's do this like this. Using Re, I will just use 3 point. You don't have to do the Re. Let's use this equation. Ln d1. d1 is 10. d2 is 5 plus 2 times 22.5 centimeter. Let's convert it into meters. Divided by, since it's the ratio, it doesn't matter. So I'm gonna keep it the ratio. 2x is 22 times 22.5 divided by d1. How much is my d1? 10. What is, can you open your calculators and help me? What is my, by the way, what is my average flow stress? K epsilon. And what is my epsilon? You remember I just told you the true strain equals to 2 times ln initial diameter over the final diameter. So let's plug it in. Open your calculators and let's do the math here. The true strain equals to 2 times ln initial diameter over final diameter, 2 times ln 10 over 5. What do you get? 1.3. Now let's round it off. And now after you do this, I'm trying to fill in this average flow stress. I'm trying to fill in for average 2 tau flow. Now you will help me. Okay, sigma y bar average flow stress is 140 megapascal. So 140 megapascal, 1.39, and the strength coefficient is how much? 0.25. Can you do the math? This is our 2 tau flow. 2 times the shear maximum shear stress. What's that? 121.6. Yes. One student verifies. That's good. So we are very close to this formula. This formula, we are gathering the variables. Okay. So I'm gonna use this formula. Look, I'm gonna grab this and then I'm gonna plug in the value. So 2 tau flow, I need the P extrusion pressure, which is equal to, this whole thing is 121.6, 121.6 megapascal times 3.414. Now open your calculators and help me. What do you get for this one? Do you get 834 megapascals? Yes. He says yes. She says yes. He says, Dimitri says yes. That's good. Now look, what is pressure? Force over area. Okay. So I can use this formula to find out the extrusion force. That is our question. The question says determine the extrusion force and then power. Extrusion force and then power. So if the speed is given, can you know that power can be found if the speed is given. You see that formula? So now we can plug it in. So let's find out what is my force. 834, 10 to the power 6. Extruded area, 5 by 4. Make sure this is the force at the back side. Okay, the force is not like a drawing force, it is the extrusion force. The backside area is to be considered for finding the maximum force. You agree with your professor? How much is it? Is it 6.6 meganewtons? And if you know that power formula, extrusion force times the speed. The speed is given in our question. It is 1 meter per minute. So can we convert it like 6.6 into 10 to the power 6, 1 meter per minute. Let's convert it in a second. Minute, minute equals to 60 seconds. So now you just do the math. And if you do the math, you get this 110 kilowatts. Can you confirm it? Yes. Now the last part says, look, determine the factor of safety. Safety factor for indenting the RAM. What it means by that, look, over here, I want to show you this diagram. Did I show you this diagram before? I think, yes. The question states, the RAM is made of high strength steel with a yielding stress of 1.5 gigapascal. So the RAM which pushes the material through the die, it has a yielding stress of 1.5 gigapascal. And what is our stress? Our pressure, uh, which is applied here. So this is my Px. Pressure can also be written like sigma x. And that is how much? 834 megapascals. Can I write down like this? Now, factor of safety says that the RAM has its own, yes. Oh, yeah, sorry about that. 834 megapascals. And the RAM has its yielding stress divided by the functional yieldings, applied stress. So what is the ratio? If you get more than one, it's a factor of safety. How much do you get? If the RAM is safe or will it break? Let's do the math. 1.5, 10 to the power 9, divided by 834, 10 to the power 6. How much? Is it 1.8? Yes? Yes. One student confirms this is 1.8. You confirm it. With that, we have finished this problem. And you should also practice. I'm going to give you some problem regarding the hot extrusion. In the hot, the average flow stress is this one. You see my point? And what is epsilon rate? It is this form. So strain, we call this as a strain rate effect. Let me bring into your notebook So you want me to share with you this handout, the PDF of this lecture? Yes? I- Will it help you to prepare? Okay, I'm gonna share with you the PDF. Don't worry about this extra slides, which you can read at home. Redundant work and chevron cracking. Sometimes we have cracking, and this is known as the chevron cracking. That's it. Defects. We call the defects. This is the theoretical, and the defects. It has like a piping effect. So we call this as a the piping effect, like it makes a triangle, a little bit cavity inside the extrusion material due to certain defects. We have to see this is, we call this a small cavity called as chevron cracking. This is just a theoretical knowledge, but the analytical knowledge is already been explained to you. Have you understood the analysis, how to apply this formula into your daily life problem? Okay, I